Hello, welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. This week we are discussing about the properties of nanomaterial, and last two lectures we have discussed the mechanical properties of nanomaterial in detail. So, today we will start with some functional properties of nanomaterial. We already know that according to dimension we classify nanomaterial into particle, rod shape, plate shape, 3D bulk structure and so on, and there are plenty of roles of this electron confinement or quantum confinement, and therefore, the functional properties could vary with those length scale or size dependence as well as on the geometry. Among all the functional properties, the electrical, optical, thermal, magnetic, acoustic, these are very important functional properties. However, we will restrict our discussion within these four types, and the detailed discussion on the magnetic properties of nanomaterial will be done in week 10. So, this week we will try to focus only on these three. So, let us start with these electrical properties of nanomaterial. Means if the size scale is in the nano level, then what is influence on electrical properties, and along the direction of electrical properties, the first fundamental principle was given by Ohm. So, we already know about the Ohm's law, and let us see whether Ohm's law can be applicable on nanomaterial or not. According to the Ohm's law, the voltage is proportional with the current, right, and there is a constant that is called the resistance R, which is equals to I by G. G is the conductance, here V is the voltage, I is the current and R is the resistance, and G is the conductance. So, G basically equals to I by V. Also, we can replace this I by V with the conductivity of the material. Okay. So, G conductance is proportional with the area of a wire. So, if it basically says if the cross sectional area of a wire increases, then the conductance also increases, as well as if you increase the length of a wire, then resistivity, the net resistivity will increase, because electron has to pass through a long path and it will encounter some of these or it will interact with some other structural defect in the wire, and therefore, their RMS and mean free path will basically will be affected, and therefore, the resistivity or let us say the conductance is inversely proportional with the length. So, length increases, conductance decreases, and here there is a proportionality constant that is called the conductivity. So, which is basically a material dependent property. Let us say in case of a copper and aluminum, gold, or let us say some other metals, they have different conductivity. Whereas, length we can change, because I can have a shorter length of a wire or I can make a longer length of a wire. And so, Ohm's law if we look at, then it basically simplifies that electrical resistance depends only on the geometry. Okay. So, geometry is basically the area and length related property, and the material based property, which is the conductivity. And in case of a nanomaterial, when the size scale is below 100 nanometer, whether it is a particle, rod, tube or plate, whether it has at all any effect on the Ohm's law, or whether Ohm's law is valid or not. So, let us say while we are reducing the geometric dimension of a wire to a nanometer, or let us say the molecular dimension? The answer is simply no. So, we cannot use Ohm's law for nanomaterial, or the law is not applicable. So, to understand this matter, we first need to understand the basic fundamental of conductivity in a material. What is the way the electron basically makes a material conductive as well as it carries the charge. So, the conductivity is basically manifested by the diffusive conductance, okay, which basically means that I have a wire of this finite length, and let us say this is the negative side and positive side. So, electron will move from one side to another side. So, electron move a path and then path, then in this way it encountered different defects, and then it basically reaches to the end. So, mean free path of the electron increases because of the scattering, and this is a scattering phenomena that I have shown, that it goes to this side, that side, and all this way. And this scattering occur because of the interaction of other electrons. So, electron electron interaction, phonon electron interaction, interaction with the impurities, lattice imperfection, or even sometimes grain boundary and so on. Now, if I keep on reducing this geometric dimension of the wire to a, let us say, nanometer level, or let us say below 100 nanometer. So, electron has a mean free path, okay, and if the length scale of this wire is in that scale, what is going to happen? So, the geometric dimension of a conductor reaches to the mean free path of an electron, then we will get a ballistic conductance. It basically says that the length of the wire is almost close to the mean free path of the electron. So, let us say here this is the mean free path, it is almost very close, and it is going to change the whole electrical properties of a nanomaterial. That is the idea. So, reducing the size of a conducting wire changes the mechanism from diffusive conductance to a ballistic conductance, okay, in nanomaterial. So, if we consider that there is no electron scattering at all. So, just electron comes here and then it goes here, and this is the mean free path, which is the length scale of a wire. So, there will be a zero resistivity, because it does not scatter at all, it does not interact with other particles or any electron or phonon. However, still some resistivity will exist because of the quantum resistance. Now, let us try to derive from the Ohm's law to a ballistic conductance in case of a nanomaterial. So, this is a typical diffusive conductance where G is proportional with A by L, and here is a conductivity component. So, G is equal to I by V, and so Q is the electrical charge. Okay. So, per unit time the charge flows, that basically gives that how many number of electron is involved with. So, N is equal to Q is the charge divided by the electron, we will get the number, okay. And V is the velocity over a length L. So, ultimately G can be expressed in terms of N E and V E by V into L, okay. And now, so if we get such a equation, then the energy actually E is equal to E into V, okay. So, where E is equal to h nu, that is the photon energy divided by the lambda. So, that is from the Planck constant we get actually. So, ultimately it lead to 1 by n and another term, that is n e square by h. And here L by lambda is basically n, which is the mode of electron. Mode of electron basically means that whether it is spin up or spin down. So, there are two possibilities. So, n is equal to 2 n. So, if we put basically n is equal to 2 n, then we get 2 e square divided by h and a constant m, which we call as a active mode in nanowire. So, m into d 0, and if you see this equation for ballistic conductance, there is no term linked with the length or the area. And also there is no sigma involved, okay, which is basically called as a conductivity. So, no longer depends on the material property, that is sigma, or the geometry means area or length, nothing. Only this h by E square, which is the term came here linked with the quantum resistance, which is something like in the scale of 26 kilo ohm and so on. So, now we understood that for a ballistic conductance in nanomaterial, when length scale of the conducting wire reaches to the length scale of a mean free path, then almost we expect close to 0 resistivity, and that is very much important, and people tried to prove it using some experiment. The experiment is very interesting. Here I show you one plot with the electrical conductivity, and here is the elongation. It basically means that one has taken a gold nanowire and the voltage was applied 32 m volt, and the length of the wire was 5 nanometer. So, this wire was straining and the conductivity and was measured, means the length is under a tensile stress and it was extending. So, there is the elongation comes, and here you see that with the elongation it shows some stepwise conductivity. The reason is the area is decreasing because the length is increasing, right. So, from 5 nanometer wire we get another 5 nanometer length change, almost like 100% plastic deformation, and the during straining at a step of 0.2 nanometer. So, each and every step is linked with 0.2 nanometer. So, the decrease of the area decreases the conductivity, as well as the stepwise movement is linked with the active mode. Okay. So, M is the mode. So, here this active mode of the nano wire also decreases, and that is why the conductivity actually decreases. That is the reason. Now, there is another very interesting experiment with the DNA. So, the DNA, the current flows through for a particular voltage, and for a 5 nanometer or 10 nanometer you can see that when the mean free path almost reaches to a 5 nanometer, we will get this is the signature of such kind of ballistic conductance. Means we apply voltage, there is the active mode, and then the active mode changes, we get more current, we get further more current, and here this is the experimental scatter actually. Whereas 10 nanometer does not show such kind of stepwise ballistic conductance, because the length scale of the wire is little bit longer than the mean free path, and that is the thing. So, the mean free path length of the electron is shorter than the 10 nanometer, whereas it is very close to 5 nanometer, that is why we get this kind of ballistic conductance. So, this is something very much interesting electrical properties in case of nanomaterial. We can also try to see that how the electrical properties varies in case of a nanotube. Okay. And whenever we talk about nanotube, the most interesting thing is the carbon nanotube, you already understood. And so, here people tried to look at the influence of carbon nanotube length on the resistance and the resistance of different nanotube. So, what they have done, they have taken a sample holder, and these are the nanotube which is basically sticked with the sample holder, and the sample holder moves into a mercury droplet, and then the current and IV characteristic is basically measured with the depth. So, if we increase the depth, means we dip this nanotube, then it is for sure that one nanotube will touch, then the length of this nanotube is going to decrease. So, here let us say if this mercury comes here, then length will change. On the other hand, now other nanotube may touch further, and then again there will be further more number of nanotube will touch the mercury, and in this way people try to do this experiment, and this is the immersion depth when 0 conductance up to a certain limit, and then there is a jump, means basically that one nanotube has touched the mercury, and continuously when we are immersion depth is increased, the length of the wire is decreasing actually. Length of the wire is decreasing means the more immersion is made. So, this length I am talking about, this length is decreasing, but there is no change of the conductance actually, you see, and again the more active modes are increasing and so on. So, each nanotube contribute equally and the conductance is independent of length. This is the typical feature of the nanomaterial, right. So, this is a very clever experiment with the bundles of multi-wall carbon nanotube pushed into a droplet of mercury. Very similar feature people have observed in case of a let us say the field effect transistor. So, in this transistor we have a silicon gate and then we have a gate insulator, that is silicon dioxide, and so in two sides there is a gold junction, in one side it is act as a source, another one is the drain, and a carbon nanotube is basically attached with that. In that case again the gate voltage and the current source and drain is basically measured. So, here also you can see that the voltage and the current, that feature is very much unique compared to the normal field effect transistors, silicon dioxide based. So, this is at a volt of 10 millivolt, and let us say here this is the 50 and here is the 100. So, this is the 10 one. So, if we increase that bias voltage, then automatically we get a current, and so we can use these single wall carbon nanotube for making these kind of transistors. Now, the third important discussion along these electrical properties is while making the nano composite, because we have a matrix and we want to improve or change or tune the conductivity of the matrix by incorporating some nanoparticle, whether it is possible or not. So, the probability of forming a continuous electrical conducting system increases with increasing the concentration of the conducting phase. Means I have a matrix and I am incorporating some nano wire or nanoparticle and so on, okay. And we are keep on increasing the concentration of the particle, okay. So, this is the P is the, let us say the volume fraction of the conducting phase. So, here we want to mean that we keep on increasing, and then if we measure the electrical conductivity versus mass fraction of nanotube, let us say P is the mass fraction here, the concentration. So, slightly it increases, okay. And then when the concentration reaches to a critical value, then there is a sudden jump of the conductivity, means the material act as a continuous phase, okay. And this is called as a percolation threshold. And after that if we further increase, then the electrical conductivity increases almost linearly with the percentage of the phase, second phase nanoparticle or tube what we are incorporating. So, reduced waste fraction means basically P minus P c, this is the reduced fraction, and the conductivity is proportional with conductivity 0 and with a power of that the reduced waste fraction. So, here this is a plot is shown in a log scale with the electrical conductivity with the reduced waste fraction P minus P c. Very so we understood that a percolation threshold or a critical concentration of the second phase nanoparticle needs in order to enhance this electrical conductivity, and beyond that the whole composite act as a continuous phase. Now, electrical conductivity we can all people have also observed by adding some graphene. So, here again the reduced graphene content means the P minus Pc which is the critical one in a polyethylene composite, and once again here you can see such kind of linear behavior when you plot in a log scale. Now, the second most important functional properties are the optical properties. So, here once again what is the role of the size of a particle and whether at all any optical properties can be modified. So, optical usually means that the visible and let us say those light which we already see in our open eye, that has a particular wavelength range from blue to red actually, and below blue means where energy is more, lambda is less. So, like ultraviolet ray, and above that red we have basically infrared which is greater than 600 to 700 nanometer wavelength. Whether we can use this nanomaterial to change some of the optical properties of a matrix, means let us say I have a matrix which has a refraction index, and if I add a nanoparticle into that matrix, is it possible to change the refraction index? The answer is yes. So, let us say for this nano composite the concentration of the matrix and concentration of the particle can modify the refractive index of the composite. Here I show you a titanium dioxide concentration with the index of the refraction n, and you can clearly see that the refraction index continuously changes from 1.52 to let us say 1.62 in a PVA matrix. So, here titanium oxide was the nanoparticle that was added, and here is the polyvinyl alcohol was the matrix. So, adding nanoparticle to a polymer can effectively change and tune the refractive index of a matrix, and this is a very good properties actually. If we really need to develop a material with a very specific refraction index, we can make a composite even to change its optical properties. Now, we already know about this Rayleigh scattering phenomena, and this scattering is also important phenomena for a transparent matrix, means I have a material which is transparent, and now I want to change some of the optical properties. So, I incorporate some nanoparticle here. Now, in that case, whether this scattering is linked with the particle size or not, or the wavelength of the light that is passing through. So, here this equation says the typical Rayleigh equation, the P scattered, P is the basically power of or energy of the scattered ray, which is linked with the constant into the concentration of the particle into n is the refractive index minus refractive index of the matrix by n square matrix multiplied by the d. D is the particle diameter which scales with the power 6, and lambda is the to the power 4. So, you can see that particle size, if it becomes small, then the net scattering could be smaller and smaller, and if we go down, then we can simply avoid scattering. So, we can prepare a transparent matrix composite even if we add some nanoparticle, because when you add a particle, the expected particle will scatter some light. So, the transparency will be lost, but below some particle size we will get a transparent material. So, let us say the smallest wavelength that our visible length actually for human eye is like 400 nanometer, which is in the range of a blue color actually, and if we add less than 40 nanometer size nanoparticle, then we can make a transparent material. So, here the thumb rule is like that lambda by 10. So, d should be somewhat close to the lambda by 10, or the largest diameter of the particle should be lambda by 10. So, that is possible. And now, we can use this nanoparticle for making some sort of UV filter. How? let us say there are two different titanium dioxide particle has been chosen. One is the pigmentary. The pigmentary has a particle size of 140 nanometer, and the ultra fine one which is something like a 40 nanometer. Okay. Both are in the nanoscale actually anyway. So, in this size side it is the ultraviolet ray and here is the visible ray, and if you see the absorption or attenuation, then the particle is basically giving the highest attenuation at a wavelength of 300, whereas the larger particle will give you attenuation in a 550 or in that range. So, I can use this nanoparticle for UV absorption. At the same time, this wider halo, okay, it basically represent the distribution of the particle size. So, the more wider particle size, it will give you a more broader size, whereas if the particle size distribution is very narrow, then you will get a more sharper peak. So, this is the uniqueness of the nanomaterial for using and tuning basically the optical properties. Now, there are some other important aspect of the optical properties, like here we see any particle they will absorb some energy and then it will emit, okay, the light. So, this is a property we call it as a luminescence. Okay. So, emission of the light and absorption of the light. Just as a schematic, I like to show you that let us say here this is a incident ray that falls on a light emitting particle, and it basically absorbs some light and then it basically emit the light. And now, depending on how delay occur in case of emitting the light after absorption will tell us whether it is phosphorescence or it is fluorescence and so on. So, luminescence is a much wider name of the property that it absorb light and then it basically emit the light. So, in case of fluorescence, the emission follows almost nearly immediately after the absorption, whereas in case of phosphorescence, here a significant time delay occur between the absorption and emission process. So, in case of this luminescence, the material is excited by a energy rich photon. So, like here it has a lower wavelength ultraviolet ray like less than 400 nanometer, and to a reduced extent the emitted as a light with a longer wavelength. So, here the lambda UV is basically shorter than the lambda of our visible light. Okay. So, this energy of the visible light is less, and so this is occur because of a quantum confinement actually, and how the effect is linked with a nanoparticle size that we are going to discuss. So, this quantum confinement is simply explained like a particle in a box. Okay. So, when I have a energy rich photon that creates a charge hole like H plus, and so I get a electron. So, I have a electron which basically rotate around this hole. Okay. So, in some case if the particle size, let us say the d, which is greater than the 2r of the excited electron or photon, then the electron will move around here inside the particle. Okay. But it may be that I keep on reducing this particle diameter and I reach to a diameter where the diameter is less than the 2r of the excitation. So, this is the excitation r actually. Now, particle cannot rotate in that way. So, here particle will come, again it will come here, then it will. So, it will be like a Brownian type of motion actually, or random movement inside a nanoparticle. So, this is the phenomena we explain in terms of a particle in a box actually. So, what is it is effect on the optical properties. So, very interesting that in the left hand side I show you a blue shift. How does it occur? We have a particle size of 2.1 nanometer, 3.2 nanometer and 7.5 nanometer. Okay. Now, 7.5 nanometer when it emits actually, so it gives you a wavelength of 650. Now, I keep on reducing the particle size, it shifted to the left hand side. So, the emitted ray, whether it will be blue or red, it depends on the particle size. This is a particle taken as a cadmium selenium, okay, nanoparticle. And so, with decreasing particle size, there is a blue shift. Blue shift means that the wavelength is coming from the or shifting from the red side to the blue side actually. Okay. So, this is why it is called as a blue shift. So, blue shift with smaller particle size. Now, I can also do the same thing by changing the composition, like here I have the same cadmium selenium particle of let us say 5.5 nanometer, and then we can change the composition to a cadmium tellurium or let us say selenium tellurium. Here this CDT particle that changes the wavelength with the composition. So, in this case we can see that we started with this cadmium selenium, and by changing its composition the wavelength changes with the composition and going towards the red side. So, this is the red side and this is the blue side actually. So, we can change optical properties due to the quantum confinement, because electrons are confined in a particle because of this effect. And once again I like to show you another example that is also very interesting. Here the same cadmium selenium zinc sulphide quantum dots. Here there are very defined particle radius like 1.4 nanometer, 1.75 and so on. So, these are the radius. So, if you multiply it by 2, that will be the particle diameter actually, d multiplied by and so on. So, 2 into r, and the wavelength that is emitted by the particle, you see the smaller the particle size, the blue will come, and the larger the particle size, the red side will come. So, this is the red side and this is the blue side actually. Okay. So, the normalized photoluminescence is linked with the particle size, and different wavelength is explained here. So, here this is a photoluminescence of a cadmium selenium quantum dot of various size. You can see with the size difference, the color of this completely changes from the blue to red and depending on the particle size. So, this is one of the very interesting functional properties when we like to change the color of a matrix, and I have already talked about this ruby glass. You can remember that the color of the ruby glass become red and so on. So, now you understand that if we add some gold nanoparticle of a specific size, and it will absorb the light and then it will emit the light, which is also one of the luminescence property, and so we can change or tune the optical properties effectively by reducing this particle size with the help of such kind of quantum confinement effect. With this today we finish our discussion. We will continue this functional properties discussion of nanomaterial in the next class. Thank you very much.